Hi. Last lecture we have discussed about two-level logic. Okay. In this lecture, let us see some discussion about the hazards. Okay. Before going about discussion about the hazards, let us understand the basic definition of the hazard. Understand, hazard is a condition where output changes. Hazard is a condition where output changes more than once for a single change in the input. Say you are changing your input one time. You have given your input may already it is there 0 or 1. You have given some input. It can be 0 or 1. You have given. Okay. Whenever your input is changed, your output will also change. It may be changed or it may be constant. But maximum it should change. If it is constant, it will not change. If it is not constant, it will change one time. But for a single input change, if your output is not changing only once, if it is changing more than once, then it is said to be hazard. Okay, for understanding purpose, see, I have a system. Some system is there. I have given some input. Okay, output is currently at 0. Okay, whenever I apply the input, it has become 1. Okay, then no problem. Okay, or whenever I have applied the input, it can become 0 only. Means depending on the input, if your present output is at 0, when you apply the input, it can be two possibilities. It can be constant at 0 or it may be changing to 1. But instead of this, if it is doing like this, for this case, instead of staying from 0 as a constant, if it is moving to 1 for a moment and coming back to 0, that is, you have changed the input. Presently, this is the output. Finally, this is the output. But in between, it is going through a transient state like this. Or here, output is changing from 0 to 1. Instead of directly changing from 0 to 1, it has gone 0 to 1, 1 to 0, 0 to 1, like this. That is, for a single input change, your output is changing multiple number of times, then it is said to be hazard. In this hazard, we have two types. This is static hazard. This is dynamic hazard. Static hazard meaning is static, meaning constant. Your output is constant, present and next also. See here, presently it is at 0, finally it is also 0. In between it is toggling, then it is called static hazard. Your output is changing but not single time. If it is changing multiple times, then it is called dynamic hazard. In the static also we have two types. Static 0, static 1. Let us see. I'll give the detailed notes. First understand the concept. Basic classification is static hazard, dynamic hazard. There is one more also. We can call essential hazards. Okay. In this static and dynamic, we have two types again. Static 0 and static 1 hazard. Dynamic also we can have two types. Essential, where it will occur. Let us see. In the static 0, meaning is output is presently at 0. When you have applied the input, it has become 1. Again, it has become 0. Static 0 hazard. If your output is toggling presently at 1, it has changed to 0. Again 1. Then it is also static 1 hazard. In the dynamic hazard, there are two possibilities. Output may change from 0 to 1 to 0 and again 1, or 1 to 0, 1 to 0. So 1 to 0 it is not changing directly, it is toggling in between. Okay. In the essential hazard, this will occur in asynchronous sequential circuits. What is asynchronous, what is synchronous at this point of time we are not discussing. Whenever we discuss the flip-flops, that is sequential circuits, I will show you what is the meaning of synchronous, asynchronous. Just for continuity, you can take this part. Okay. What is sequential circuit? What is asynchronous sequential circuit? When we discuss about the combinational and sequential circuits, I will give you clearly. Okay. Now, these two will occur in combinational circuits. This will occur in asynchronous sequential circuit. What is this combinational and what is sequential circuit? Just for continuity, understand. Combinational circuit is nothing but here the output depends on input only. It is not having any memory. In any system, output depends on only on input, not having any feedback or memory. Then we call it as a combinational circuit. In the sequential, output depends on input and also previous values. It will be having the feedback or memory. Okay. We'll see those circuits when we discuss the respective chapters. Okay. Just for continuity, understand these are the different hazards we have. I will give you example and how to eliminate these conditions also. First, keep the heading hazard. Keep the heading hazard. Hazard. Write down. Hazard is a condition. Hazard is a condition where output changes. Hazard is a condition where output changes more than once. Hazard is a condition where output changes more than once for a single change in the input. For a single change in the input. For a single change in the input. Next line. Hazards can be classified into following types. Hazards can be classified into following types. Please copy this. I'll give the definitions also. Just for first copy this table. Classification. Right. Now write down first one. Keep the side heading static hazard. Static hazard. Write down. In that subheading, static zero hazard. Static zero hazard. Write down. Static zero hazard. Static zero hazard occurs. Static zero hazard occurs. Static zero hazard occurs when the output is presently at zero. When the output is presently at zero, due to the change in the input, it becomes 1, and again becomes 0. It becomes 1 and again becomes 0. It becomes 1 and again becomes 0. It becomes 1 and again becomes 0. Next. Write down. Next line. Is it clear? Static zero hazard means presently output is at 0. When you give the input, it becomes 1 and again it becomes 0. Write down next line. In a properly formed formed AND OR logic, in a properly formed AND OR logic, there is no AND OR logic, there is no static zero hazard. There is no static zero hazard. There is no static zero hazard. Next line. Next side heading. I will explain that. Okay. If it is a AND OR logic, it will never occur static zero hazard. Okay. Next line. In a properly formed OR AND logic. One second. Keep the side heading. Please remove the line. Write down static one hazard. Keep the side heading static one hazard. Okay. After this line, in a properly formed AND OR logic, there is no static zero hazard. Next side heading static one hazard. Write down in the static one hazard. In the static one hazard, output is presently at 1. Output is presently at 1. Due to the change in the input, it becomes 0. Due to the change in the input, it becomes 0. And again 1. Okay, same as previous, but here output is presently at 1. Next line. In a properly formed OR AND logic, two-level logic you can understand. In a properly formed OR AND logic, there is no static one hazard. There is no static one hazard. Okay, static one hazard will not occur in the OR AND combination. Next line. Static hazards can be eliminated. Static hazards can be eliminated by adding redundant terms. Static hazard can be eliminated by adding redundant terms. I will show you with example how we can eliminate that hazard. Okay. Next, keep the side heading dynamic hazard. Write down dynamic hazard occurs when the output is changing from one state to another state, but it changes more than once for a single change in the input. Next line. Next line. Dynamic hazard occurs due to different propagation delays of the data path. Next line. In general, if we eliminate all static hazards, dynamic hazards will not occur. Next line. Both static and dynamic hazards will not change the output permanently. Both static and dynamic hazards will not affect the output permanently. They will affect only temporarily. You can understand here. Here finally your output is again coming to its original value. Yes or no? In both these cases. Okay. Here also. You want 1, it will come 1, but in between it is going through a transient state. So your output, whatever you are expecting, that output will come. It need not be same, it can be different also. System, as per system function, you will get the output, but in between it is changing. It is not affecting your output permanently, it is affecting only temporarily. Okay, but please understand, in this essential hazard, your output will be permanently affected. So they must be compulsory eliminated. We should take care of this condition, because it may affect your system response differently. You are expecting some output, you may get different output because of this kind of essential hazards. Okay, write down this, keep the side heading, essential hazard, essential hazard, essential hazard. Write down. Essential hazards occur in asynchronous sequential circuits, which will affect the output permanently. We must avoid essential hazards. It may affect your output permanently, okay, because the system output may be affected permanently. So we should avoid this essential hazards. Okay. Now let us take one example of this hazard, and let me prove that it can be eliminated by using redundant terms. Please understand here one important condition. Why these hazards occur? We understand what is hazard. Okay, now what are the different hazards? But why they will occur? Please understand. Why they will occur is because of different propagations. When you give the input, to get the output in between, all the signals may not pass through equal amount of delay. One signal may come first, one signal may come later. Because of this different propagation delays, we will be getting the problem here. Okay, let us see. Let me take one function. Okay, so this is my function. This is A, B, A. So you can understand this bubble is one inverter. My function y equal to AB plus A bar C. What is y? AB plus A bar C. Okay. Now let me take initially my input is your A, B, C is 0, 1, 1. Okay, what is A? 0, 1, 1, 1. Okay. Now, what is the output I'll get? 0 into 1. What is the answer? Otherwise, 1 second. First, let me take 1, 1, 1. Sorry. A, B, C, all are 1s, for example. Now, 1 into 1, what is the output? Say, for example, let me take this gate is having a propagation delay of 1 nanosecond. What is the meaning of propagation delay? Earlier also we have discussed. After giving the input, it requires some time to get the output. That time gap between applying the input and getting the output is called as propagation delay. Okay. Here also, say because the two gates are there, let us assume randomly 2 nanoseconds, because one inverter, one AND gate. And it is also having some delay, some TZ, it may be, okay, some delay is there. Now, suppose this is my condition, 1 into 1, what is the output? 1. 1 bar means what? 0. 0 into 1, 0. 1 plus 0, what is the answer? 1 plus 0, my output is equal to 1. Say this is the condition when t less than 0. Already you are having this output. Okay. All of a sudden, at time t equal to 0, I made ABC, I changed my input to 0, 1, 1. What happens? Let me check. So at t equal to 0, I made it A0, B1, this one 0 and C1. Now you see, this gate requires how much time? 1 nanosecond. So at 1 nanosecond, what is the output? See, you have applied input at 0 time. After 1 nanosecond, you will get the output. What is the output you will get? 0 into 1. What is the answer? 0. Next. Here, 0 bar, how much? 1. Is it clear? Inverter is there. 0 bar is 1. 1 into 1, what is the output? 1 will come. But what is the delay you are having here? 2 nanoseconds. So, whatever you apply the input, it will give me the output after how much time? 2 nanoseconds. Before 2 nanoseconds, you don't get the output. So, at 1 nanosecond, your output is same as the previous value. Very important, please understand. Your output is, you can understand, this gate output will change after applying the input. It requires how much time? 2 nanoseconds time is required here. Okay. But here, this requires only 1 nanosecond. So when you apply the input here, first this will change, but it will not change immediately. It will change after some time. Up to that, it will be in the previous value. Now 0 plus 0, what is the answer? OR gate operation. 0 plus 0, what is the answer you will get? After some delay, whatever may be, you will get 0. Okay. Now, at t equal to, say, 2 nanoseconds, as the input is not changed, output will be as it is. But now, you understand, when you apply the input at 0, how much time it requires? 2 nanoseconds. At 2 nanoseconds, this input will give me the output of 0 bar. What is 0 bar? 1 into 1. 1 into 1, what is the answer? So 0 plus 1, what is the answer I am getting? 1. Now you can observe here. You have changed your input A from 1 to 0. Your output is at 1 presently. Because of the change of the input, just for a moment it is going to 0, and after some time it is coming back to 1. This is the final value your output is. This is the present value, next value. In between it is maintaining some going to 0. This is called as static one hazard. Why this has occurred? Because this A need to travel through 2 nanoseconds propagation delay, but here A will be traveling through 1 nanosecond delay only. Because of different propagation delays, this will occur. This is an example of static one hazard. Please copy it. Okay. So in the previous lecture, in the previous case, whatever I have given the statement, I have given you one important point. What is that? We can eliminate static hazards by adding redundant gates. By adding redundant gates, we can eliminate static hazards. Let us see that. What is the meaning of redundancy? See, do you remember consensus law? According to consensus law, AB plus A bar C is also equal to AB plus A bar C plus one more you can add redundant term is BC. What is this? Redundant term. You can understand. Yes or no? AB plus A bar C plus BC is equal to AB plus A bar C. This is what we discussed in the consensus law already. So I have added one extra term here. Now the same circuit, how it will work, let us see. So it may not be the same every time. Okay, it may not eliminate all hazards. Sometimes it may be possible. For that particular input case here, it is possible. Now if you take BC. Right. Now I have added one. Still my function will be same or different? Same, because of the consensus law. Yes or no? AB plus A bar C plus BC is same as AB plus A bar C. So I have added B and C here. Let me check what happens. As we discussed earlier, initially the output is 1. See here. B and C are initially 1. At t equal to 0, how they have changed? Same gate delay you take it, 1 nanosecond. You can understand BC may there is no change. Initially 1 1. Now also it is 1 1 only. So 1 1 is changed with 1 1. Only A is changed. Now B into C, how much? B into C, 1 into 1 is 0. When you apply the input, what is the delay you have here? 1 nanosecond. After 1 nanosecond, what is the output I will get? After 1 nanosecond, 1 into 1 again, 1 into 1 is 1. Okay. After 1 nanosecond, because the input is not changed, the output will not change. 1 into 1 is again 1. 1 into 1 is again 1. Now add here. 1 plus 0 plus 1 OR operation, output is 1. 0 plus 0 plus 1, what is the output? 1. 0 plus 1 plus 1, 1. So is there any hazard here? Your output is not changing in between. This is how we eliminate the hazard. This is no static 1 hazard in this case. That is how we eliminate hazards, by adding a redundant gate. Okay, redundant gate means that gate should not change your function. We are adding one extra gate, the function will be same. Okay. So here I applied by consensus law. Later we see by K-map also we can add redundant terms. So by adding this, because BC is not changing in both the cases, output will be 1 for the AND gate, and addition will always give you 1. So in between it is not going through 0. If your function output is changing to 0, it will change, but in between it is not going here. So we have eliminated the static 1 hazard in this case by adding redundant term. It is proved. Now please copy it. Copy totally again. Let us take one more question on this hazards. Okay, or let us take the one more question based on delays, propagation delays. Write down the question. In the logic circuit shown in the figure, the logic circuit shown in the figure, the non-inverting buffers, are having propagation delay of 2 nanoseconds, 2 nanoseconds and 4 nanoseconds as shown in the figure, and 4 nanoseconds as shown in the figure. If the input A applied at the input of the circuit is the waveform shown in the figure, then determine the number of times the output changes. Determine the number of times the output changes in the first 10 nanoseconds. Determine the number of times the output changes in the first 10 nanoseconds. Please understand, the propagation delay of the non-inverting buffers are 2 nanoseconds, 4 nanoseconds. If the input applied is as shown in the figure, then determine the number of times output changes in first 10 nanoseconds. Just one more line you add it. XOR gates are not having any propagation delay. Assume XOR gates are not having any propagation delay. Right. Please copy the figure and this waveform. Just take time equal to 0 to 11. He is asking up to 10 nanoseconds. Time is in nanoseconds. Okay, right. Let us try this question. Before going to try this question, what is the meaning of buffer? What is the meaning of non-inverting buffer? Non-inverting buffer means if you give input x, y is also same as x. Okay, but if the buffer is having some delay like this 2 nanoseconds, so if you are giving x here like this, but I'll get this x after how much time? 2 nanoseconds, I'll get the same. That is the meaning. Delay, buffer. Delay is nothing but shift. Okay, right shift by required amount of time. Please understand. Suppose any buffer means output same as input. Okay, whenever buffer is having some delay, then the output is same as input after that particular amount of delay. How we show the delay? By shifting in the time domain. Okay, so now use this concept. Here, firstly, examiner has given that two buffers are having the delays of 2 and 4 nanoseconds. You can understand here. Let me take some variables here. This is A. This one is A1. What is delay? What is the meaning of A1 here? A1 is nothing but same A after 2 nanoseconds. What is this? Let me take it as X. This is X. What is this one? X1. What is the meaning of X1? X1 same as X but after 4 nanoseconds. Please understand the meanings properly. First let me draw A1. What is A1? A1 is the same as A but after how much time? 2 nanoseconds. So A has changed at 1. 1 plus 2 is how much? 3. So A1 will change after how much time? 3 nanoseconds. You get the same figure but after 3 nanoseconds. Okay, this is your A1. A1 is the same as A but it will come after how much time? 2 nanoseconds delay. This is A1. What is A1? Delay A by 2 nanoseconds. Next, let us see the next one, X. What is X? X is nothing but XOR operation of the two inputs of XOR gate. What are the two inputs of XOR gate? X is nothing but A XOR with A1. Okay, here no delay is there. If delay is there, first we find without delay and shift it. Is it clear? If XOR gate also having delay, we first find the answer without delay, then shift it by required delay. But here there is no delay for the XOR gate. Just XOR these two. What is XOR? Here it is 0, 0. What is XOR operation of 0 and 0? It is 0. Here 1, 0. What is XOR operation of 1 and 0? 1. Here it is 1, 1. What is the XOR operation of 1 and 1? 1 and 1 XOR operation is 0. So you can understand it is initially 0. Here it will become 1 and again becomes 0. This is A XOR A1. There is no delay here. Okay. Up to this clear? First A delayed by 2 nanoseconds, A1. Both are XOR. You got this. Next. What is X1? X1 is nothing but, one second. X1 is nothing but delayed version of X by how much time? 4 nanoseconds. Say here it is 1. Here it is how much? 3. Delay 1 by 4 nanoseconds. 1 plus 4 how much? 5. Delay 3 by 4 nanoseconds. 3 plus 4 how much? 7. So this is same as this but delayed by 4 nanoseconds. So what is X1? Delay X by 4 nanoseconds. Now see here. Final answer, output Y. What is your output Y? Y is XOR operation of its inputs X and X1. X XOR with X1. Okay. You can understand here. You tell me. Here it is 0. This is 0. 0, 0 XOR is 0. Here it is 1, this is 0. 1 and 0 XOR is 1. Here 0, 0 XOR is 0. Now this is 0 and 1 XOR operation 1. This is 0 and 0 XOR operation 0. 0 0 XOR is 0. 0 1 XOR is 1. 0 0 is 0. 1 and 0 1. 0 0 0. So here initially it is 0. After some time it has become 1. Again 0 1 and 0. This is your output expression for x XOR with x1. That is nothing but your output y. Yes, okay. You can understand here how many times, what is the question, how many times output has changed in first 10 nanoseconds. Here 0 say 1 time. Here 1 to 0 2 times. 2 again 0 to 1 third time. 1 to 0 4 times. So output is initially 0. After applying your input, it has changed how many times? 4 times it has changed, and again it has become 0. It is also one kind of static zero hazard. It has changed more than once for a single change in the input. It has toggled and finally settled at 0 again. So this is the output function. How many? What is your answer now? You can understand how many times it has changed? 4 times. Okay, copy it. One second, you can understand here the same question you can do without drawing the waveforms, but it will be difficult to analyze. You may be end up with confusion. Here the input changed or not. Okay, so sometimes it is better to draw the waveforms. Okay, if the circuit is not complex, if it is simple like our previous question, we can analyze with the zeros and ones directly from the figure itself. So according to your convenience, you can draw the waveform, or you can take directly the zeros and ones at the input accordingly. That is, here you take 0, it has changed to 1. How it has changed with respect to time, you should write the answers. It will be confusing here. Okay, so if you draw the waveforms, you never confuse. Okay, you can understand all steps. Just I'm revising. You can understand what is A1 delay A by 2 nanoseconds. So shift this A by 2 nanoseconds. Finish. Next, what is X? XOR operation of these two waveforms 0 0 0 1 0 1 1 1 0. Like that you XOR both, you got this. Next, what is X1? See the figure. X1 is a delayed version of X by how much time? 4 nanoseconds. So shift this signal by 4 nanoseconds. 1 shifted by 4, it will be 5. 3 shifted by 4, it will be 7. If you want, you can write here also. It will be 5 and it will be 7. Then last one is XOR these two, 0 and here 0. 0 0 will give you 0 in the output. 1 0 will give me 1. 0 and 0 0. 0 and 1 1. 0 and 0 0. So how many times it has changed? 4 times. Copy it.